Hi Calc, this is section 2.2 number 33. We're going to graph this function and then look at where we can find the limit and where we cannot. So this particular function is called a piecewise function. If you recall, the functions are in this column and the domain restrictions are in this column. Okay, so for this particular case, there are three functions that are cut and pasted together to make a new function. So I'm just going to start by rough sketching these functions. Alright, so the first function is a parabola. It's at the origin. I'm just going to rough sketch a few points on it. Okay, that's our first function, which is the parabola. Let me just say y equals. Okay, the next function, that's linear. So whenever you do a linear case, see if you could just graph the intercepts. So like if x is 0, y is 8. If y is 0, x is 4. And then the last function, y is 4. A line where y is always 4 is horizontal. That means that every point is at a height of 4. Okay, so that's the first part. Those are the three functions that are going to be cut and pasted together to make the original function. So now let's do the domain restrictions on it. So for this function, you have to cut it at 2. So you actually want to put 2 in there. So you want to do like 2 squared is 4. So that means when x is 2, y is 4. Okay, and it's open, it's closed because it has the bar. And you want to take everything less than 2. So things less than 2 go to the left. So this tells you where the function is turned on. And everywhere else it's turned off. So I'm just going to go now to drawing the final graph. Okay, so we've got the point 2, 4. And I just added a couple other points. I'm using the concept of symmetry to do it. This guy is closed on the left. Alright, so that's the part of the parabola that transfers over. Now for this guy's going to get cut between 4 and 2. Now notice it doesn't include 2 or 4, so you've got to just be careful of that. So at 2, you got to actually plug 2 in here. So 8 minus 2 times 2, which is 8 minus 4, which is 4. So at 2, when I put in 2, I get out 4. So at 2, 4, which is about right there, it's open because it doesn't include 2. There's no bar here. Okay, and at 4, I already know that. That's 4, 0. That's also open. So it's going to look like that. It's going to take everything in between 2 and 4. Alright, so I'm already using 2, 4. So if you have an open and a closed, you don't draw an open on top of a closed. It means it snaps together and it's just closed. Okay, so that one snaps together and closes, and then this is me connecting. So this is the segment here that I have. Okay, and the last one you're going to get where x is greater than or equal to 4. It's closed at 4, and it keeps going. Okay, so at 4, we're going to be at a height of 4 that's closed, and it keeps going. Okay, gang, so this is f of x. This is the original graph. I broke it down so you can see how I got there. Okay, so now let's talk about limits. So at this point, the 3 things that I'm stressing that I want you to have memorized is that the two-sided limit fails to exist at a vertical asymptote because it's unbounded, at a gap, and at an increasing oscillation, right? And I was trying to also stress when I went over the homework that the limit does exist if there's just like a hole in the graph. Just on, it's all connected, but there's just a hole somewhere, okay? So if you notice, there's no discontinuities here. I wouldn't fall through the graph anywhere. I can take the limit everywhere, here, here, and here. But the minute I get to 4, I've got this gap. And as we know, if I come in from the right, I'm up here. As I come in from the left, I'm down here. So the heights of these 2 points don't equal each other or approach each other, which means that the limit would fail here. So you have a limit everywhere on this graph, including here. You can have a limit at like a sharp point like that, because from the left and the right side, they're both going to the same destination. But at a gap, no. So the limit here exists everywhere except at x equals to 4. Let me just say it that way. Limit exists everywhere except at x equals to 4. So so the limit as x goes to 4 on this function is a dne because you have a gap. Okay, so I can take the limit anywhere on this graph except at this one spot here. Okay, if that's confusing you, I'll do a couple for you if that would be helpful. So for instance, the limit as x goes to 0 of this function. So on the left side, the height approaches 0. On the right side, on the right side, the function approaches 0. On the left side, the height approaches 0. So at 0, it approaches 0. Okay, so for instance, that's the limit there. The limit as x goes to 2 on this function, right? The limit, I can find the limit anywhere except at a gap. So as I go to 2 from the left and the right side, so as I go to 2, as x goes to 2 from the right side, the height goes to 4. As x goes to 2 from the left side, the height goes to 4. So the height is going to 4 on both sides of x equals to 2, so therefore it's 4. Right, and you can do this anywhere on the graph. The limit as x goes to -1 on this function. So here's -1. We're going to come in on both sides of this x value. So as I come in from the right, the height goes to a +1. As I come in from the left, the height goes to a +1. So the limit of that is +1. So the idea is if the function is continuous, you can find the limit there as long as you're not at a VA, a gap, or an increasing oscillation. Okay, so again, this graph has limits everywhere except where this gap is right here, because the heights don't approach each other. Okay, gang, I hope that helped. I'll catch you.